All right, today's date is November 24th, I think, right? And we're starting 10-1 in algebra. And we're still kind of in this part of reaching back to grade 7 algebra and re-exploring the things you probably learned but maybe didn't put words on. And we're just talking about it again so you understand your grade 7 algebra in order to give you a chance to learn grade 8 algebra. So our topic today is 3 ways to solve algebraic equations. And the first way, we're going to call it solving by inspection. Okay, and solving by inspection is simply asking yourself, asking what number is missing to make both sides equal. Now this doesn't really make sense until I give you an example. And there's different ways to define it. In fact, every time I've ever defined inspection, I've defined it a different way. But today, this is what I'm going to use for my definition, asking what number is missing to make both sides equal. So for example, in one of the easiest algebra questions we could possibly muster up, x plus 1 equals 3. If I asked myself, instead of saying x, I said what number? So if I said what number do you add 1 to it to get 3? Or what number plus 1 is 3? So if I ask myself that question, what number plus 1 is 3? What is the answer going to be? 2. The x is going to be, the answer to that is x is going to be equal to 2, or x is 2. We solved that without using any kind of magical algorithm or any kind of procedure or any kind of systematic approach to getting the answer. We just ask ourselves, well, what number does x have to be if x plus 1 equals 3? X is 2. And we could use this idea of solving by inspection. If I gave you this question, then the question I would ask myself is, what number multiplied by 2 is 6? So what number multiplied by 2 is 6? Question mark. And what number do we multiply by 2 to get 6? 3. So our answer for this one is x is equal to 3. 2 times 3 is equal to 6. And again, in order for us to really be able to read that, we need to know that this is a coefficient and this is a variable. And a coefficient variable relationship is always multiplication. When you learn back in our integer unit, if I said 2 bracket 3, when you have a number next to another number, that implies what operation? Multiplication. The same thing is true, the same idea is true when we have a number next to a letter with no brackets. It still implies multiplication, just like the other one did. And I'll give you one more example by inspection. If I did x over 3 equals 1, what question would I ask myself to make this work? What number divided by 3 is 1? Does everyone see that this equation up here and this sentence being the same thing? Do you guys see that? What number divided by 3 is 1? And Calvin, what number divided by 3 is 1? Or what number divided by itself is always 1, right? Any number divided by itself is always 1, correct? So therefore, x has to be 3. That's your answer. 3 divided by 3 is 1. Okay. So that method that we used here works really, really well for simple algebraic equations where you can look at it and you can say, what is the answer? What does x have to be? X is 3, x is 1, x is 2. Whatever it happens to be, we can always figure it out just by asking ourselves, what is the answer to this question? That's our first method, and I want you to be aware of it because we do use that frequently with easy questions. The second method is called modeling. And I'm not going to go too deep into what it means, but it's representing equations as balanced drawings. And the funny thing is, if I look at my definition from this morning's class, that would be completely different than than what I just wrote now. So representing equations as balanced drawings. So if I give this idea of 2 plus 1 equals 3 again, as a drawing, it would be an x and a plus 1 equals plus 3, right? And I say, okay, I want this scale. The scale is equal. And I have my x plus 1 equals 3. And I can kind of see with this picture, what does that rectangle x tile have to equal in order for those two sides to be equal? It has to equal 2, correct? So we can even use our it's an easier way for maybe sometimes to see the answer to the equation as being x equals 2. But what we actually do to solve it is we apply opposite operation. And right here, by putting a -1 on both sides, in algebra, what you're asked to do is understand that whatever you do to one side of an equation, if you do the same thing to the other side, regardless of what it is, if it's doubling it, if it's cutting it in half, if it's adding 1, if it's subtracting 1, whatever you do to one side, if you do the same thing to the other, it maintains balance. But the reason why we added a -1 to the equation was because it creates this zero pair. And pictorially, what I've done is I've isolated my variable. And what does that simply mean? It means that I've got my x by itself on the left-hand side. And over here, because I added -1 to that 3, it actually canceled 1 out, and I'm left with just 2. And if I read my solution as a picture, it says x is equal to 2. And I got the same answer as I did in the inspection, but I did it with a picture instead of a question. Does that make sense? What was the second example I gave you up top? It was 2x equals 6, correct? So if I take that same question, 2x equals 6, and make a drawing, then I have 1x, and I have 2 x's, right? That's 2 of those rectangles, which represent x values or unknown values, is equal to 6. And if I think about I'm going to use positive 6, so if they're shaded in, that's positive. My marker is not overly sophisticated, so it doesn't know the difference. If I put it up like that, it makes inspection a little bit easier too, doesn't it? If 2 of those rectangles is equal to 6 dots, or 6 positive integer chips, each of those rectangles is equal to how many? 3. We know that through inspection. But through a drawing, if I divide both sides equally, if 2x is equal to 6, then each of those x's has a weight or a value of 3. And all I did was I divided both sides equally onto 2 separate scales to find the solution that x is equal to 3. Same question. Okay? Does that make sense? So our third one we had was x over 3 equals 1. So x over 3 equals 1. Now, actually, when I said x over 3, I didn't say what it says. I said what it looks like. Does anyone know how I could read this properly? Instead of saying x over 3, what's a better way to read that? We could say x divided by 3. Or better yet, a third of x. So instead of having a full x, I only have a third of x. Because if I divide something by 3, I cut it into thirds, right? So x divided by 3 is really a third of x. So if I'm drawing it, and that rectangle represents an x, I'm not going to shade it in like I did over here for a full x. I'm only going to shade in a third of it. That's not quite a third, but we'll pretend it is. Okay, so that's how much of x I have. I only have a third. And that third of x is equal to 1. Now, if I ask the question, how many thirds of x do I need to make it equal to a full x? What would the answer be? How many of those would I need? How many of these right here would I need to have to make a full x? 3. So this idea of the algebraic scale works really well for this picture, because what I'm going to do is I'm going to double it, and then I'm going to triple it. So what I ended up doing was just tripling the weight of that side. And if I'm going to keep that equal, I'm going to triple the weight of the other side. Put another one there and put another one there. And this picture now shows us the solution, because if I think about what all 3 of these together would make, it would make a full x, wouldn't it? Is equal to 3. Let's just be shaded in. And we have our solution of x equals 3. If I go back and just to double check, and instead of having an x, I put a 3 there. Is 3 divided by 3 1? Yeah, so x is equal to 3. So those 3 methods that we used here are what we would, in the mathematical profession, call concrete representations or pictorial representations of algebra. And you are responsible for being able to look at an equation and be able to represent that with a picture using a balance of scale and be able to isolate the variable through pictures only. Okay, so that's part of the outcome. You won't use it. You won't use it in your day-to-day algebra life, whatever that happens to be, because you will always use method 3, opposite operation. But you still have to understand how it works and be able to draw it. Okay, which brings us to our final one, which is the third method for solving algebraic equations, which we're going to call opposite I spelled opposite wrong. Opposite operations. I'm always feeling like I should have put two P's in operations as well. You'll hear me call it op a lot, especially on tests. As I solve with op. Op simply means opposite operations. And opposite operations, solving an equation with opposite operations and solving it with modeling is exactly the same thing. There's no difference. The only difference between solving it with opposite operations is I don't use pictures to represent what I'm doing to both sides. I use numbers. So if I take that first question, which was x plus 1 equals 3, x plus 1 equals 3. If I think about what I did just real quick in my picture, what did I do here on both sides to my picture when I solved it? What did I put on both sides? I put an opposite to the constant. I put a minus 1 on both sides, right? I put a minus 1 on both sides. And the reason why I do that is because I'm isolating the variable. I'm getting x by itself because this part of your equation is called a constant. It's the plus minus value. We talked about it last day. And by putting a negative 1 on both sides, I'm keeping it equal, but I'm getting rid of that constant and I'm isolating the variable to be x. And if I ask myself, what is the combination of 3 and negative 1? It's positive 2. So if I think about that solution right there, everything I just did numerically or with numbers is the exact same thing I did right here pictorially, right? I added negative 1 to both sides and I got my solution of x equals 2. No difference. If I think about the other equation, what was the other one? The second one was 2x equals 6. What did I do in my picture when it was 2x equals 6? Here was my 2x equals 6. What did I do here? I divided everything I had into two different scales, right? So if I go back down here, I divided this into two piles and I divided this into two piles or two groups. Then I can say to myself, these are opposite operations. This 2 represents multiplying by 2. This 2 represents dividing by 2. And those are opposite operations. So I put a line through it and I get x equals 3, right? So I've solved that equation by simply applying opposite operations to both sides. 2 times 3 is equal to 6. X has to be 3. And the final one I had x over 3 equals 1. And if I think about what this looks like, just to remind you real quick, because it wasn't that long ago, it was a third of x is equal to 1. What did I do to both sides in that equation pictorially? I tripled it, right? I multiplied both sides by 3. And if I multiply this sides by 3, I'm going to use a bracket 3. And technically, it's that. So keep your 3 in a bracket to show multiplication up top there where the numerator would have been. And bracket 3 over here, because whatever you do to one side, do to the other. Those are opposite operations. If you triple a third of x, you get x. And if you triple 1, you get 3. So those are my three solutions using just opposite operation.